Thank you very much for the introduction, Dr. Carter. I also would like to thank Dr. Carter and Professor Chen, Zhongwei Chen, for inviting me here today. I'm particularly pleased to have this opportunity to give a talk at your institute, WIN, W-I-N. That is the exact same as my short name. Okay, so I feel very excited to give a lecture, at your institute. So it's also my great pleasure to have this opportunity to talk to you on some work that we are doing, okay? For the new membrane for CO2 separation and hydrogen and the water purification. Let me see. I had all right. Okay, moving in the right direction. That's good. I will talk two types of a membrane today. One is carbon dioxide selective membrane for hydrogen purification for fuel cell, and then I also will cover the interfacially polymerized reverse osmosis membrane for water purification. As you may know, that currently, there are technologies, for carbon dioxide separation. Okay. Certainly, the most commonly used is the amine swabbing process. Personally, I also work on that while I was at Exxon, as Dr. Carty mentioned earlier, that we are very fortunate we are commercialized, for processes, using, the different kind of stereocrate hindered amine. But however, I recognize that, that's a quite cumbersome process. I will see it more, and also require, the solution regeneration. And since there are also other, technology such as, adsorption by use of a GLI or some, the other adsorbent. But for all those, they all involve, two-step thermodynamics equilibrium controlled, processes. Okay, for one for either absorption or, adsorption, and another one would be for regeneration. Okay. Here shows the schematic diagram for the aqueous amine solution swabbing. So your free gas coming in, concurrently in contact with aqueous amine solution, and all the solution then go to the regenerator for regeneration. You can see that you need to pump the solution between the two towers. It's rather cumbersome operation. So then certain other there are some emerging technologies, including the use of a membrane contactor that provide a very high surface area, mass transfer surface area per unit volume. And also, they do use also aqueous amine solution, for the separation. And again, it's still two-step thermodynamically controlled process. So we are thinking, how about we convert this cumbersome operation, into a simple pressure-driven process where free gas is introduced to one side of the membrane, And then if membrane is designed in a way that's selective to carbon dioxide for going through, and then this will simplify, a lot of operation. We don't need to pump the solution back and forth, okay? And so here it shows SEM, of a selective membrane on the top, and then supported by nanopores support, and then in the bottom you have a non-woven fabric, for mechanical support. Those is a typical type of structure, and that's also the membrane that we try to we have made in the laboratory, and now we try to scale up for the practical application. You may ask what are the advantage, for using the membrane process versus the amine square. So first of all, since there's no solution regeneration involved in the membrane process, in the membrane process, both absorption and regeneration take place simultaneously. One's on free side, and other one's on the polymer side. And so this simplifies the process. And also the membrane module typically is quite compact. That means has very high packing surface area and per unit volume. And also quite lightweight. Okay, so particularly for the offshore platform application, different is quite advantage. As mentioned, the simple operation is a pressure-driven process, and if membrane is stable, then there's no additional chemical is required, and also it's a kinetic process, so it's not limited by the chemical equilibrium. Actually, I believe I'm blocking some of the view over here. Maybe a table is too big. Okay, let me see. If we can move this one to the side. Okay. And if I can get out of your way, I may not block anything. That's good. So the bottom line is, hopefully, it will be a more economical process. As you know, that fuel cell works well if you have a high purity hydrogen. So today, the cheapest hydrogen really comes from the natural gas, through the steam reforming. But unfortunately, any of those carbonaceous material, we're going to deal with carbon monoxide. Okay, and so for the fuel cell to work well, we like to have a carbon monoxide to go down to less than 10 parts per million, 10 ppm, and hydrogen sulfide is another poison that preferably to get down to less than 10 parts per billion. Certainly, this presents a quite challenge to the fuel cell application. So we want to see what we can do, to solve this kind of problem. And so the water gas reaction is also always involved when you deal with carbonaceous material. As you see, right now we're getting hydrogen from natural gas and some from petroleum. And the near future it will be the coal and biomass. For some in biomass got disappeared here. It's also the future hydrogen source. So for all those carbonaceous material, we must deal with water gas shift reaction. Try to convert carbon monoxide to have that react with steam to produce more hydrogen and get the carbon monoxide to go down as low as possible. Unfortunately, this reaction is reversible, so that if it is about 1%, typically about 1% of unconverted carbon monoxide. That's what's been used, today in the refinery operation. So they do have to use other steps in order to deal with carbon monoxide, including methanation, okay, and so they're going to consume the hydrogen in order to do that. So we got to deal with carbon monoxide cleanup. So our approach is to use a carbon dioxide selective membrane that can remove the carbon dioxide, and that will increase the concentration of hydrogen. Typically, as you know, you contain about 20% of CO2 in the syngas derived from methane. If you from coal, then the carbon dioxide could go up to 40 some percent. Okay, so it's very significant that when you remove the CO2, you can increase the hydrogen concentration significantly. And then with the CO2 selective membrane, now we hope that we can drive this water gas reaction to the completion to get down to less than 10 ppm, and then hopefully we can also decrease the hydrogen sulfide. So you may wonder what kind of a membrane is going to do all those tricks. Okay, so I'll give you one example over here. We take a polyvinyl alcohol as a polymer matrix, then in which we incorporate the amino group into the membrane. And the amino group will react with carbon dioxide reversibly. So at the high pressure side, that react in the reaction product can then transport across the membrane, and then the CO2, because of reversible reaction, is then released to the low pressure side. Okay, and that also regenerate the amino group. This so-called preceded transport. Essentially, we're using chemistry to enhance the mass transfer. But however, something like hydrogen and also other gases, such as carbon monoxide and also nitrogen, if they are nitrogen, they are particular case, if air as oxygen source for doing the reforming reaction. So all those will be blocked by the membrane because they cannot react with amino group. Okay, and so even though CO2 is a much bigger molecule, because of reaction, then can go to the membrane much faster than hydrogen. Here I plot the CO2 hydrogen selectivity versus the CO2 permeability in bar. Okay, I think later on I will show you the unit of bar. So initially, we make a membrane from polyamine. Okay, this amino group is so-called non-sterically hindered or unhindered amine. Then we obtain the results over here. Okay, it's not bad, but we believe we can do much better. Then we make a membrane from this polymer. Actually, we modify the polyamine through the reaction, and that we introduce the isopropyl group to this nitrogen side. With this modification, this so-called sterically hindered amine, based on the definition of a degree of steric hindrance, these fall into the so-called moderately hindered amine. Because of the presence of a bulky group, the amino group reaction with CO2 is affected because not enough space for the carbon dioxide to attach to the nitrogen side. So this, when CO2 attached to the nitrogen side, you make a so-called carbamate. Okay, because the carbamate is unstable, due to the presence of bulky group. So this carbamate is then hydrolyzed readily, to form bicarbonate, and also that also regenerate this amino group. So for the hindered amine, you would have a much more free amino group for reaction with CO2 in comparison with this unhindered amino group. Since unhindered amino group, the carbamate formation is stable. The carbamate is stable, and then carbamate would dissolve. We have a proton to come out, and proton got to find another amino group to neutralize it. So essentially, in order to absorb 1 mole of CO2, that consumes 2 mole of amino group. But here, we can achieve the theoretical limit, of 1 mole of amino group to absorb 1 mole of CO2. Okay, so therefore, the performance is enhanced significantly. You can see this, more than double, both in selectivity and also on the permeability. But if we increase the stick hindrance to further using an even bigger group, this tertiary butyl group, and so this group is so big, the CO2 cannot even approach to the amino group. So the reactivity difference is reduced significantly. But because of more free amine group, than the unhindered, so the performance is still better, than the unhindered. But certainly it's not as good as moderately hindered amine. Here I have a same plot, but include some of the data that membrane based on a solution diffusion mechanism without any chemical reaction, so without the amino group in the membrane. Those are data that surveyed by the DOE, Department of Energy, the NETL, National Energy Technology Laboratory. Okay, so you can see if based on a solution diffusion mechanism, that the CO2 hydrogen selectivity is relatively low. And there are some data on the literature published result on the free-sheet transport membrane. Some of them, those higher ones based on our earlier work. And then our work over here, blue is for the free-sheet transport membrane with the polyiamine I showed earlier. And we push this performance to higher and higher when we introduce the stick hindrance amino group, so we can push to a higher performance. Here shows again the similar plot. Here the permeability. I did give you a unit of bar over here. This is in memory of Professor Robert Bauer of Imperial College. This shows the permeability versus the temperature on this plot, and then the selectivity is on this side, on those lower plot. So the permeability is very, very high when the temperature is not too much higher than 100 degrees Celsius. But when the temperature increases to much higher, the permeability reduces. And that's because the membrane's ability to retain the water molecule inside the membrane reduces as the temperature increases. When you go too much higher than the boiling point water molecule want to come out. Okay, we do need a water molecule in the membrane in order to enhance the reaction between the CO2 and amino group. Okay, so that's why you see the performance coming down. But even so, that even at 180 degrees Celsius, the permeability is still pretty high. And the selectivity is also quite good. And typically, most applications we encounter, particularly for the fuel cell application, that fuel cell is typically operating at 100 to about 140 degrees Celsius. So in this range, both permeability and the selectivities are pretty good, and that's where our scale-up work will address for the hydrogen purification for fuel cell. And I did mention earlier that the CO2 react with two more of unhindered amino group form a carbamate. Okay, so this carbamate is stable. Certain carbamate is stable if you use unhindered amine, but when you use the sterically hindered amine, then the carbamate is unstable. As I said, then this would hydrolyze bicarbonate, as a sink for CO2, and that also regenerate the free amino group. For reaction with hydrogen sulfide is rather different. Essentially, is acid and base type of reaction that involve the proton transfer, from the acid hydrogen sulfide to the amino group. Because proton is a very small moiety, so the reaction rate is not affected by the steric hindrance. So in fact, the hydrogen sulfide can go through the membrane even faster. I show you a result over here. That hydrogen sulfide can go through the membrane about 3 times faster than CO2. Okay, so this allows us to remove the hydrogen sulfide first before we get into water gaseous reaction. And so here I said that from 50 ppm hydrogen sulfide containing syngas, we're able to get down to about 10 ppb of hydrogen sulfide. Essentially, we remove all the hydrogen sulfide. So we can remove the hydrogen sulfide before we do the water gaseous reaction. Now, as you may know, almost all the catalysts available today for water gaseous reaction is all very sensitive to hydrogen sulfide. It would be poisoned by hydrogen sulfide. So it's good to remove the hydrogen sulfide before we do the water gas reaction. So here we put the catalyst, on the top of a membrane. So the catalyst will catalyze the water gas reaction, and then membrane, will remove the CO2 to go across the membrane. And because we designed the cell in a way we know the geometry exactly, so we can calculate the gas flow rate and the gas velocity, and we can use for the modeling comparison. Here we took a syngas composition containing 1% of carbon monoxide. As I say, that's most of a refinery would be able to give you this kind of carbon monoxide concentration through the conventional water gas reaction. And this is a typical composition if we use gasoline, as the hydrocarbon source, then it goes through the autosomal reforming, using air, as the oxygen source. Then you also introduce the nitrogen. So based on the modeling calculation, which I do not have time to go into detail, but your interest, we have several papers published in this area, that shows we'll be able to take 1% of a carbon monoxide to go all the way down to less than 10 ppm. So on the paper looks good, right? So the reason we can achieve that is really through the removal of CO2, by the membrane, and that drive the water gas reaction. Usually we remove CO2 from 17% to less than 1400 ppm. So on the paper, that looks good. Experimentally, we use exactly the same syngas composition, and so the carbon monoxide concentration, in the hydrogen product that we produce, the majority of them is less than 10 ppm. So depending on the size of membrane, if we use a bigger membrane, we'll be able to push the flow rate to higher, okay, which can be done. And comparing with our modeling calculation, it's reasonably good since we're following the same trend. Okay, we also we try to remove the carbon dioxide. Okay, we're able to remove 17% of carbon dioxide. We're able to get down to about 30 ppm of carbon dioxide, in the syngas. Essentially, we can remove, almost all the carbon dioxide. If we use steam as a sweep gas, certainly some refining plant and even some power plant, they do have a so-called waste steam, those low pressure steam. If we use that as a sweep gas, and then you condense after the membrane process, then you condense the steam, we obtain more than 98% of CO2 concentration. Certainly that's good, higher than the DOE target of 95%, for the carbon sequestration. Okay, so the membrane will allow us, to do this. All right, let me shift the gear to the to the reverse osmosis membrane. As you know that for reverse osmosis membrane, any species, particularly sodium chloride, salt, that's what we try to use membrane to reject. And so we hope to produce the high purity water. The transport mechanism is still through the so-called solution diffusion mechanism. And the drying force is the applied pressure subtract the osmotic pressure, okay? That provide the drying force. There are quite few commercial applications, certainly for the desalination of blockage and the seawaters, concentration of juice from California when they ship to New York, for example, and the wastewater treatment, and also in the electroplating plant. So there are quite many of those applications. The typical membrane structure here shows a schematic that you have this non-woven fabric, okay, and your microporous membrane support, typically made of a polysulfone, with a pore size of about 50 nanometer. And then you do the interfacial polymerization to make this selective layer. Typically is about 0.2 micron. So the here is a quite well-known process using the interfacial polymerization. Now you take the nanoporous polysulfone, and then you coat the first layer of an aqueous diamine solution, and then after that, then you do the interfacial polymerization with acid chloride and hydrocarbon. Okay, then you make this our membrane. Here is the chemistry invented by John Cadat, okay, who worked for FilmTech, then they don't become a Dow Chemical. So it react MPD, methyl diamine, with a trimethyl chloride, and then you make this interfacial polymerized polyamide. So there's about 72% you have this cross-linking linkage, and then here is that the third group is not reacted, then they don't hydride, become a carboxylic acid group. But we recognize that this membrane is very, very tight. Okay, we see all those high degree of cross-linking. And the most importantly is that we figured the hydrophilicity was not high enough really to give a high flux. So we figure maybe something we can do here, to improve the flux. All right. So before we embark this research, we did in our laboratory, we tried to reproduce John Cadat's work. John Cadat's work that was commercialized. In fact, this is a state-of-the-art membrane today. So they can produce about 25 gallons per square foot of membrane area per day, GFD for short, and with salt rejection of 98.5%. This is for the brackish water that contains over 2,000 ppm of sodium chloride. We reproduce their procedure. We did in our laboratory. Come pretty close. We can say that's we pretty much reproduce what John Cadat could do. Okay, and we did that in our laboratory. So now we see how about if we introduce another group with a hydrophilic group moiety compound during the interfacial polymerization. So this hydrophilic group will be incorporated into the membrane through the covalent bonding. So membrane that will be stable, inside the membrane. And the rest is identical. Okay, so this is only chemistry, that we change. Here we show you the SEM of nanoporous polysulfone. The typical pore size mentioned somewhere in the order of about 50 the nanometer. And here is a top view, of the surface of interfacial polymerized polyamide. You can see a lot of those boron type. Okay, you see those are membrane. Okay, so people say because of this kind of topology, that increase the surface area significantly. That also enhance the flux. Okay, but that was a typical surface look like. And when we did the cross section, so it's difficult to see. You see the interfacially polymerized layers over here. It's somewhere in the order of about 0.2 micron. So I think this one shows a little bit better contrast. Okay, it's in the order of about 0.2 micron. So the hydrophilic additive that we put in during the interfacial polymerization is also aminobenzoic acid, amine salt. And so we start with the John Kada's teaching. Without our additive, we obtain about 22 GFD that we saw earlier. And when we increase that, then see significant increase on the water flux. Okay. Then if we increase further, we put in too much in there, and they seem to reduce. And so that, when you put the additional compound to the reaction mixture, obviously they're going to change, your reaction. They're going to interfere the interfacial polymerization. Okay, so we define the optimal concentration. The salt rejection is also pretty good, correspond to this, pretty well. So, obviously the hydrophilic additive provide a, additional pathway for the water molecule transport, because the membrane is much more, hydrophilic, and we do need to go through some other additional step, including some so-called pore treatment, including drying. So we are able to improve the flux to 52 GFD, and salt rejection is also, pretty good. And we start from the laboratory size, which will make about 3 inch, by 3 inch coupon. And then we make to we call the laboratory scale up. We make to 10 inches by 10 inches. And then we further scale up to the commercial size. We work with a membrane company. Essentially, we rent their production machine, okay, to do the scale up. So this is about 42 inches wide, and we make 1,000 feet. So the performance for scale up, it remains pretty good. We can scale up quite nicely. This is rather unusual. Sometimes, sometimes we may encounter some of scale up issues, but here we're quite fortunate. We're able to scale up those membranes, and then we work with the company to make this into a spiral wanded module. This is a 4-inch diameter and 40 inches long. Before they ship to us, they wrap in the foil. Okay, that. So we make 12 of those membrane module, and their productivity is about 4,300 gallon per day, for the membrane area. And that membrane area is about 82 square foot for the each module. Average out, the flux is also in order of about 52 GFD. So essentially the module performance, that correspond to our laboratory result pretty well. The salt rejection also pretty good. Then we ship those modules to Bureau of Reclamation, and then they did the test, in Alamogordo, New Mexico, and they confirm our high flux result. Here I show the membrane stability running for 30 days. The flux remain quite stable, and then salt rejection is also pretty good. Okay, those for the brackish water. When we did the FTIR for the membrane before the test, and also did the one after 30-day test, it's pretty much identical. So we did not see much of a change, according to the FTIR. When we run the membrane with different salt concentration, as I say, brackish water about 2,000 ppm of sodium chloride, and our membrane performance over here. When you increase to the higher salt concentration, you increase the osmotic pressure. When we apply the same pressure of 225 psi, so obviously your flux gonna drop somehow. Okay, but it's not bad. Versus the commercial membrane, the sample we obtained from a company, so we show the significant, increase the flux. We essentially about double, and then the salt rejection is also better. Then here is we run the 2,000 ppm of sodium chloride concentration at a typical brackish water desalination pressure, and then those flux is over here, and then here salt rejection is over here. Those are data that we saw earlier. But because the flux is higher, that will allow us to reduce the pressure, okay, to save the energy. So if we reduce the pressure, so then obviously the flux is going to drop, okay, but still, pretty decent, okay, for the flux. Then if we use low salt concentration, still maintain at a low pressure, so the flux will increase slightly higher, okay? Drop the concentration, reduce the osmotic pressure. The salt rejection is still pretty good. Then we could further reduce. This could be used at home. Typically, the city water, we have 70 to about 100 psi of pressure. And the flux is still pretty decent. Salt rejection is also pretty good. So those are the results for membrane. And we compare that with those membrane on the market. Now, you go to Dow Chemical, you can buy the extra low energy membrane. The performance over here is lower than what the membrane that we can make. Okay, and then if you buy from hydronautic, it's called energy 7 polyamide, third generation, that is over here. So they are all lower than what our membrane can achieve. Then if you run at a low pressure, 150 psi, is a Dow Chemical brackish water. Okay, then this would be actually this is actually this membrane is running at 225 psi. So this flux certainly is much lower than what we can achieve. Then if you run the hydronautics membrane at 150 psi for the 1500 ppm salt solution, the result again is below what we can achieve. Even the salt rejection is also lower than ours. And then you run Dow's extra low energy, and at 100 psi, at 500 ppm. 500 is much higher than most of city water that you will get. Okay, then we also shows better performance. So in summary, that for the fuel cell membrane, the CO2 selective membrane, now we have synthesized a membrane that shows a high CO2 hydrogen selectivity, and we're able to achieve about 10 ppb of hydrogen sulfide in the hydrogen product. And then we use a membrane in conjunction with a water gas reaction. We're able to get down to 10 ppm of carbon monoxide in the hydrogen product. And that's very good for the fuel cell application. For the reverse osmosis membrane, so our new membrane can obtain a flux of 50 gallons per square per day. And that's about 100% higher than the one based on Jiang Kadat's teaching. Our initial scale-up is quite successful. We can make to the commercial sites, and the membrane stability is pretty good, and we also show the improved performance versus the market product. Before I close, I would like to thank some of my students and some postdocs for the fuel cell, and also for the reverse osmosis. And Dr. Normandy and Dr. Richard Song, they provide us some of the microporous membrane support. And I'm working with Doug Wheeler. He's doing the equipment design for the hydrogen, the purification process scale up. We like to thank National Science Foundation, Offering Naval Research, Ohio Department of Development, and Ohio State for the financial support. I leave you with the Nature Bridge. So hopefully we can contribute to some, green engineering to the our society. Thank you very much for your attention.